Thank you everyone for coming to this JGI and Heilbronn seminars. This is the last one of the term. As you know, we've been inviting Turing Fellows to give talks this semester, and we're very fortunate today to have Professor Nick Whiteley. So he is Heilbronn Chair in Data Science. He's obviously the fellow of the Turing Institute and co-director of, director of Compass. And so he got his PhD from Cambridge, and he became a lecturer at Bristol quite early in his career, I believe. I know that his CV at the time was really quite intimidating. And I know this because I went for the lectureship position at the same time as him. So I was very pleased to see that his research output was so impressive at that time, because it's good to get beaten by somebody so obviously competent. So it's really great to have him talking here today on the statistical origin of manifold structure in data. Please take it away, Nick.
Thank you very much for such a kind introduction as well. So let me just share. Things are going well. So hopefully now you can see my screen. Does that work? Done? All good? And can you see the little pointer hand thing? Excellent. All right. Thank you. Yes, thanks for the kind introduction. I think a lot of what will be talked about this week, JGI Data Week, will be about recognizing and extracting and interpreting structure in data. And the structure that I'm going to talk about is geometric structure. So this is structure which is expressed in terms of notions of shape and length and area and volume. But it's going to turn out that it's also in some way structure which is quite statistical or probabilistic. So related to ideas of uncertainty and dependence and correlation. So overall, the work that I'll talk about is about bringing those kind of two types of structure together. And part of what I'll talk about is based on some recent work with Annie Gray, who many of you will know is a PhD student in the Compass program here in the School of Maths, and my colleague Patrick Rumdelanchi, also here in the School of Maths. And there's a little bit of sort of sneak preview of some new material that's not in that paper, but if anyone wants to talk to me about things that are in the slides, just let me know and I'll be happy to have a chat. So, as I said, this talk is about geometric structure and statistical or probabilistic structure, and about trying to work out a connection between those two types of structures, partly motivated by this, which is informally known as the manifold hypothesis. And as we go, I'll tell you a bit more about what is meant here by a manifold. But I thought, to start off, I'll just show you a few pictures to get a bit of intuition going. So, assuming that you've passed that statement that's written on the screen, let's have a look at some examples. So we have a data set which is a collection of 72 photographs, digital photographs, each grayscale, of a car, and they're taken from different angles around a circle in the horizontal plane. Now, each of the photographs turns out to have this many pixels in it, so we can view each of the images as a vector of this length. And what I've done here, for reasons which will become a bit clearer later, is that I've just reduced the dimension of that data set down from this fairly large number down to 3 dimensions. And what you see on the right is something which is clearly got a lot of structure to it, right? The points that we get by applying the dimension reduction using PCA roughly speaking, they appear to be in a loop of some sort. I mean, evidently it's not exactly a circle, but it's something like a loop which has been twisted and perhaps bent. And moreover, bearing in mind that each of the pictures was taken sort of at evenly spaced locations around the unit circle, as we traverse this loop, well, the points we get from applying the dimension reduction, at least in places, look to be more or less sort of evenly spaced. A bit difficult to see what happens as we go around the corner here, but things are spaced apart. And so there seems to be, after having applied PCA, some sort of signature, perhaps, of the physical domain, which was underneath the mechanism by which these data were captured. Okay, and this kind of structure in sets of images is very well known. In fact, people have been doing computer vision now for quite a long time, and so this is to people with computer vision experience, this kind of structure will be very well known. But what I think is not so well understood, or has not been explained in a very detailed manner, is, well, other than at the sort of heuristic level that I just talked in terms of, this idea that this seems to sort of visually resemble the physical domain underlying these data, well, why should we get specifically this sort of twisted and deformed shape? I don't know. Why should it be the case that the dots along here seem to be roughly evenly spaced when pictures were taken from roughly evenly spaced angles? Is there any sort of credence to any of that at all? So that's just one example which I'll to bear in mind as we go. As a second example, so a different kind of data. These are this is a data set which consists of a temperature time series. So it's from 2,211 cities around the globe, and the dots here just tell you the locations of the cities. And for each city, there are 1,450 daily average temperature recordings. So what's mean daily average? It means the average over a 24-hour period, and there's 1,450 24-hour periods. The coloring here, by the way, it's nothing to do with temperature. This is just colored by latitude. And then again, applying PCA. In the bottom row, this is what you see if you reduce down to 3 dimensions, just from 4 different viewpoints, so that you get the impression that there's some sort of segment of some kind of ellipse appearing. And if you just project down to 2 dimensions associated with the first 2 principal components, you see something a bit circular there. And the reason that I've colored things by latitude is that you see that there seems to be a connection of some sort between the latitude of the cities, and perhaps even something to do with the distance around this curve, perhaps. Again, there's some sort of semblance of the underlying physical domain, which is appearing in the data. All right. Okay, so another example, which is perhaps it's not so easily explained just purely sort of in terms of physical intuition. So this is from a paper that was published in Nature a few years ago, back in 2008. And it's genetic data related to 3,000 people who are Europeans. And the data are genotyping basically of a quite large number of sites, this large number, and then reduced down to just 2 dimensions using PCA. And quite remarkably, a picture seems to emerge where the first two principal components seem to convey some structure which is related to the underlying geography, or at least that's what the authors of this paper would like you to put together, right? So all that's happened here, just to be clear, is that the coloring on this points over here is just identifying the nationalities of the people involved. So once again, Okay, we've had some fairly high dimensional data. We've collapsed it down to a small number of dimensions with PCA, and we see some structure which seems to resemble something about the physical environment, if you like, in which the data were captured or generated in the first place. Oops. And one more example. Now, this is it's another genetic example in some ways, although in a bit of a different way. This is data that's related to gene expression. So for 23,000 cells, 3,000 genetic features were recorded, and those are then reduced down to 50 dimensions using PCA, and then down just to 2 dimensions using something called t-SNE, which, if you don't know what it is, it's a type of nonlinear dimension reduction technique. And for these kind of data, as I understand it, the scientists are interested in understanding how the genetic features are related to the functions of the cells in question. So the coloring in these plots conveys something about what type of cell it is. For example, excitatory neurons or inhibitory neurons, or something which is not a neuron. And there's an important feature of this example, which is different, which is in contrast to, well, two important features of this example, which contrast with the examples I've shown you previously. In the previous examples, the underlying sort of structure, which was visible when we then performed PCA, was something to do with physical location or geography. Right, and I chose those examples just because physical location or geography is quite kind of often easy to sort of imagine and visualize. Here, it's the underlying structure, or the structure of interest, is nothing to do with physical location or geography. It's something abstract, right? The structure of interest is cell type. Okay, but nevertheless, it appears to be that there's something in the geometry of the data which reflects those cell types. And the second important feature is that, as I mentioned, in this case, the data are first reduced in dimension with PCA down to 50 dimensions, and then down to 2 dimensions just for purposes of visualization using t-SNE. And what's shown here is the picture that you get if you just go directly down to 2 dimensions using PCA. Okay. And part of the interest in these nonlinear dimension reduction techniques is that, by first going down to moderate dimensions in a sort of linear way using PCA, and then going down to a small number of dimensions using things like t-SNE, we can seem to be able to do a better job of separating out these clusters of cell types. And if we just go directly down to 2 dimensions with PCA, the classes are all sort of on top of each other. Okay, so it seems there's a hint that the interesting structure is in higher than 2 dimensions. In fact, it's higher than 3 dimensions, right? If I plotted the 3-dimensional PCA, again, things would all be on top of each other. Fine. So in all these examples, there's been various types of data. There's been various types of underlying structure, whether it's been something physical or geographic, or something a bit more abstract and sort of discrete, such as cell type. And that latent structure seems to have manifested itself in what we see in the data. Now, I mentioned in the introduction the idea of the manifold hypothesis, and to go a little bit further, I now need to tell you what I mean by a manifold. So now things start to get a bit more mathematical. Some definitions first about homeomorphisms, diffeomorphisms, and isometry. I'm going to think about them in the context of where I've got 2 spaces, and in order to be not overly abstract, they're each going to be metric spaces, so spaces which have some notion of distance associated with them. And, well, homeomorphism, diffeomorphism, and isometry are basically defined as it's stated here. But I'll show you some pictures to give you a little bit of intuition about what these things mean. So first, thinking about to try and get some everyday intuition for a homeomorphism. imagine that I start with this shape, this pointed star, and it sort of it's shaded to indicate that there's some relief to it, so you can think it's actually a 3D object. And imagine this thing is made out of some pliable material like plasticine. Okay, and suppose that I'm going to deform this plasticine star by any transformation which involves bending, twisting, stretching, or compressing, but without any puncturing, that is, without creating any holes, and without any tearing. Okay. Well, any such transformation would be a homeomorphism. So, for example, moving from this star to this rounded off star would be a homeomorphism. A diffeomorphism requires something a bit more than that. And in everyday terms, a diffeomorphism rules out the possibility of any sharp edges being added or removed. So we're basically not allowed to start with a smooth object and end up with a rough one. So this sharp star is homeomorphic, but not diffeomorphic to the rounded off star. And this rounded off star is diffeomorphic to this sphere here. Okay. And here's some more examples. So again, starting from the left, I imagine that I have a plasticine teacup and that I'm allowed to deform it by squeezing and bending and twisting, but not by tearing or puncturing. Well, that's a kind of classical example that I can get from there to a torus by a homeomorphism. Back here. But then what's the story about going from here to here? Well, what I described, transformations that are just defined in terms of bending and twisting and stretching, well, those are, if you like, those are sufficient conditions for a transformation to be a homeomorphism, but they're not necessary ones. Okay, so if you have a little look at actually what the definition of homeomorphism is, what does it say? Well, imagine that I identify some point over here in my torus and identify some second point over here in my torus, and I join them up with any continuous path. Okay, so it could be jagged or smooth, but just any continuous path. Right. And then a homeomorphism requires that once I map those 2 points in the path between them over to here, I still have a path which is continuous. All right. And what does a diffeomorphism mean? Well, if I'd started off with a path which is not just continuous, but which is smooth, for example, differentiable, the path I get when I project it over again is equally smooth, basically. Okay, so from here to here, assuming this is a cup which has sharp edges to it, that would be a homeomorphism, but not a diffeomorphism between that and the torus. From here to here, it will be a diffeomorphism. And from here to there, it will be a homeomorphism because we've created sharp edges in moving from here to there and back again. Okay. Now, of course, I've claimed that these are homeomorphic and diffeomorphic and so on. I haven't proved or conveyed to you exactly what the supposedly existent phi is that maps these things to each other. You'll have to trust me a little bit on that. But later on, we'll see a situation where we will sort of get our hands on some maps which do give us quite explicit definitions of some homeomorphisms and diffeomorphisms. But there's just one more example that I want to talk about, which is when I show it to you, it'll probably seem a little bit mundane compared to these kind of exciting things, but it turns out to be one that's on one hand sort of practically very relevant, and on the other hand conveys some of the mathematical generality of what's going on here. And it's this example. Okay, so now let's say U is just a discrete set containing these 3 points. Okay, and I need it to be a metric space, so I'm going to endow it with this thing called the discrete metric, which says that 2 points are at distance 0 if they're the same, and otherwise they're at distance 1. It's a well-defined metric. And over here, I've got 3 points, and they're in Euclidean 3-dimensional space, and they're all different. Okay, so I could have a map, right, which has the in subscripts suggests, just identifies A with VA, B with VB, and C with VC, and then U and V are homeomorphic. Okay, so you know, if I go back up to here, often when people talk about homeomorphisms and diffeomorphisms, they have in mind, or at least they show these kind of pictures involving sort of continuous surfaces and what have you. The mathematical generality goes much more beyond that, and it's important we need to include, for what I'll talk about later, discrete things. And this then takes us to the question of what a manifold is. Right. Well, let's suppose that we've got two sets M and Z, and that they have metrics associated with them. Well, M is called a topological manifold if it's locally homeomorphic to Z. So that just means that if I look at any point in M, that means I can find a neighborhood of it, which is homeomorphic to the neighborhood of a corresponding point in Z. And similarly for a differentiable manifold, it's diffeomorphic. Actually, the local nature of these manifold definitions will turn out not to be super relevant for what I'm going to talk about later. I'll mostly end up talking about sets which are globally homeomorphic to something. So don't worry about this local bit for now. It won't show up too much more. Good. So now I can talk in a little bit more detail about this idea of the manifold hypothesis, and I wanted to convey the extent to which it has permeated statistical theory and methods, mostly in about the last 15 to 20 years. I'm sure it's been thought of long before that, but in the last 15 to 20 years, and it's got a lot of attention. And there's various statistical methods which are out there, which are explicitly, or in some cases implicitly, predicated on this idea that there's manifold structure present in data. And the first collection of them is methods which are sort of just designed to pull out the manifold structure itself. Right? So trying to estimate the dimension of an embedded manifold, or just to perform a hypothesis test that a manifold is present in data in the first place. There's ideas of nonlinear dimension reduction, which TSNE, which I mentioned earlier, is one of those. And generally the idea with these is I imagine that I have data which are point clouds which are concentrated around some manifold, and these nonlinear dimension reduction techniques seek to in some sense sort of flatten out those point clouds, so in order for them to be visualized or analyzed in lower dimensions. Then there's families of methods which are designed to perform classification regression on manifolds, by which I mean situations where covariates are assumed to lie on a manifold. And then in connection with the discrete example that I mentioned a moment ago, in a way, we can also view things as like clustering, as being predicated on some kind of manifold structure, right? At least if you accept that this is a manifold in a certain sense, right? It's a topological manifold because it's homeomorphic to this. Then there's a sense in which performing clustering is predicated on manifold structure. Clustering is arguably about sort of recognizing connected components. And if we go more general than that, that takes us into the realms of topological data analysis. So of course, to go through all these in detail, it will probably require a full lecture course. And I'm going to just point to 3 papers which take different angles on it. Larry Wasserman's paper on topological data analysis, which is, if you know his work, you'll understand that it's a rigorous but pragmatic view on many of these ideas. If you prefer the sort of machine learning vibe, then there's a paper by Benjo et al. On representational learning from 2013, which I find quite stimulating. A little bit of time has passed since then, but it's still very relevant. And if you like a more purely mathematical viewpoint, then there's a paper from Charles Pfefferman, who I think quite a few years ago, he won a Fields Medal, not in the context of statistics or anything really statistical, but he has a paper on designing a hypothesis test for the presence of a Riemannian manifold in data. Okay, so main message here is just that this idea of the manifold hypothesis has permeated rather quite a lot of methodology and theory. And another thing which is it's important for me to highlight is that when you look into how many of these methods are both theoretically sort of set up in terms of the assumptions that they rest on, and how people often implement them in practice, a lot of the time, PCA for dimension reduction is used as a front end. So just like in that RNA example that I showed you, often people will start up with some very high dimensional, sort of, well, you know, thousands, millions, perhaps, of dimensions, bring that down to something 50, 100 dimensions using PCA, and then do some of these things like nonlinear dimension reduction and regression and classification, or clustering or TDA. And that sort of PCA front end, I don't think so far it's been really explained why, from a statistical point of view, that's really a good idea, or perhaps not in the way that I'm going to talk about next. It's often just motivated as a computational convenience, right? That the original data are so high dimensional, we need to do something a bit lower dimensional to have hope of applying something like these nonlinear dimension reduction techniques. So PCA as a front end is a thing that I want to keep in mind. Fine. Now on to the work that I've been doing with Annie and Patrick. And the roadmap for what I'm going to tell you next, it looks like this. I'm going to show you something that we've called the random fields and latent variables model. Okay, and what is it? So it's a statistical model, and you'll see that it's doesn't have a lot. It doesn't have very prescriptive, for example, distributional structure to it. Okay, what we're trying to achieve is to postulate generic statistical structure, which we hope can explain a wide variety of data sets, rather than trying to write down a really precise model to represent some specific data set. Okay, and to draw a little bit of a parallel, although without wanting to be ostentatious about this, if you think about, say, the law of large numbers, okay, so there is a model underlying the law of large numbers that the random variables in question, say, are IID. Okay, and perhaps that IID-ness would sometimes just be called an assumption, but you could view it as a model. All right, and what we're trying to do with this RFLV is similarly to come up with a model which is sort of free of specific distributional assumptions, or as free as possible. And moreover, the mathematical phenomenon that I'll tell you about also has some connections to the law of large numbers. So what I'm going to show you is that under this RFLV model, the PCA scores, and I need to tell you what the PCA scores exactly are in a minute, but that those things are concentrated around a manifold. And the key thing is that we can show that this manifold structure emerges, even though the definition of the random field latent variable model doesn't involve any explicit construction of a manifold. And so we'll show you that this manifold structure just sort of emerges, it turns out, due to mathematical interaction between some latent variables and some correlations. Okay, so let's go. What is this RFLV? It looks like this. We've got a data matrix, which is of size n times p, right? And that data matrix is built in terms of 3 independent sources of randomness. And the first source is a collection of n random variables. They're latent variables, meaning we don't observe them, or we assume we don't observe them. And they come from some distribution, let's call it mu, which is supported on Z, which we're going to assume is a metric space. Okay, so some set which has associated with it some notion of distance. Okay, and the second component is a collection of random fields. Okay? And there are p of them. So this is equal to the dimension of the data, if you like. And what do I mean by a random field? You can just think it's a real valued random function. Each each of these x's is an r-valued random function, and each of them has domain z. Okay, so if I fix some little z in here and I evaluate the random field at that point, that's a random variable. Okay, I'll explain a little bit more about the interpretation of these things in a moment. But the third component is what I'll describe as noise, which is something that we're going to add on. We're going to assume these noise variables are zero mean, unit variance, and we're going to have a sigma out of the front, which is going to allow us to play with the size of that noise. So, modulo some mathematical structure or assumptions, which I'm going to add in a minute, basically that's it, right? That's what this random fields latent variable model is. And so what do I have in mind for each of these ingredients? So what about Z? Well, think about that example with the images of the car. Okay, so I have in mind in that case that this Z could be the circle of positions from which those photographs were taken. Okay, or in the context of the global temperatures, Z could be the surface of the Earth. Okay. Or in the context of the DNA example, Z could be Europe, okay? Or in the RNA example, Z could be the discrete set of cell types. You remember we had like inhibitory neurons, excitatory neurons, and neuron, okay? And there's one of these Zs associated with each index 1 up to n, the sample size, okay? And the interpretation of the random fields is that for each field, I could, in principle, evaluate the field xj, say, at any location z in my latent domain, but that's not exactly what I observe. What I observe is the latent field evaluated at a point specified by the latent variable. Okay. And we add some noise, largely just for generality, to explain something in the data which might not be captured in this way. And I'll talk about some different instances of this model in a minute. But again, here comes a bit more of the mathematics. To be able to say precise mathematical things later, we're going to assume that Z is compact. These two assumptions are perhaps I think in my view, for the mathematics to work, more important, although perhaps not strictly necessary to make appear the phenomena that I'm interested in. I'm going to assume that each of the fields are independent, although not necessarily identically distributed. Okay, so note that does not mean that the features associated with one particular data point are independent, because we're evaluating those fields at a particular Z, but evidently there's some conditional independence there. And moreover, we're going to assume that the correlation function, by which I mean this mapping, for each field is continuous with respect to whatever notion of distance is defined, associated with this metric space. Okay, and lastly, the noise terms are going to be assumed to be uncorrelated across I and independent across J. All right. So that's the random fields latent variable models. Now a precise statement of what I mean by principal component scores. These were basically the things that were being plotted in the illustrations of PCA earlier. These were instances of these things. So we start off with our data matrix. We fix some R, which is less than P and less than N, and we find the orthonormal eigenvectors associated with the R largest eigenvalues of this thing, which is up to rescaling by 1 over n, 1 over n. This is the correlation matrix. Now, often when people apply PCA, they'll have centered their data. So you can either think the data have already been centered here if you like. Actually, it turns out that centering it's not really critical for what I'm going to go on to say. But you can think of this thing as a covariance matrix, if you like. And the PCA scores, what are they? They're basically what I get when I take the inner products between the data vectors and each of these eigenvectors. Okay, so zeta I is the vector of coordinates of the ith row of y projected onto that subspace. So a little picture to explain what's going on. In this case, right, no surprises, the first principal component is in this direction, the light dots being the original data, the dark dots are what we get when we multiply the V1 by each of these principal component scores. Okay, in the case where P is 2 and R is 1. Okay, so the principal component scores, they're the coordinates, but in the system defined by the eigenvectors of interest. Okay. Okay, sorry, I'm just trying to. Okay, brilliant. Fine. Right. Now, what we want to do is to study the behavior of the principal component scores under that random fields latent variable model. And there's one stepping stone towards that, which is an application of Mercer's theorem. And that's something which says that if I take any kernel, so it happens to be a kernel, this particular kernel, which I'll call the mean correlation kernel. Okay, and by mean, what do I mean? I mean this average and correlation in this way, that there is a feature map which allows me to write this mean correlation kernels as infinite dimensional inner products, infinite dimensional in general. Okay. And so this is the representation of kernels in terms of feature maps, or at least one instance of it, which is sort of sometimes called the kernel trick, or related to what's called the kernel trick in kernel methods, right? But it's just a representation theorem. I've got this average correlation function. I can express it in terms of inner products. And here we go. So Y comes from the random field latent variable models. And I'm going to assume something about the moments of the random fields and the noise variables involved. Okay, so I've got some Q which tells me how big I can take bigger moment I can take that is finite in each case. And a bit of a simplification here is that I'm going to assume that this mean correlation kernel here has a rank R. And then if I happen to take the R dimensional PCA scores, well, what can be shown is that up to transformation by an orthogonal matrix Q and rescaling by square root of P, the principal component scores are uniformly, in the sense of this maximum, concentrated about this feature map phi evaluated at the latent variable Zi. Okay, so we'll explain a bit more about what the interpretation of this bottom thing means at the moment, but just with a quick glance at what's going on here, we'll see that theory says that we're guaranteed of this happening with a certain probability if n is large enough, and if also p over n is large enough. Okay, so we're in a situation where having high p is sort of helpful in terms of making sure that this happens. All right. Fine. So in summary of just what was on the last slide, under this random fields latent variable model, PCA scores are concentrated near the images of the corresponding latent variables through the feature map phi. Okay. And of course, those points, phi of Z1 up to phi of Zn, they're points in this set I'm going to call M, which is just the image of the entire set Z through phi. Okay. So what this is saying, or what the result on the previous slide is saying, is that the PCA scores are, if you think of them as a point cloud, if you like, they're uniformly concentrated around around this set, specifically concentrated around these points. And now we can say a little bit more about this set M, and as you might guess from the fact that it's written as M, it's going to turn out to be a manifold if we introduce a little bit further structure, specifically via this thing that I've called the distinguishability by correlations condition. So what does it say? It says, I take any point Z and Z prime in my latent space, in latent domain, that are not equal to each other. And I ask whether or not I can distinguish between those points in the sense of comparing correlations, or at least sum of correlations against some sort of test point psi. Okay. Now, it turns out that if this distinguishability condition holds, phi, this feature map from Mercer's theorem, can be shown to be invertible. Now, in general, even if I were to have a sort of nice closed form expression for this thing on the left-hand side, in general, I don't have a nice closed form expression for phi, the Mercer feature mapping in general. But nevertheless, it's going to turn out that we can say quite a bit more about phi and its connection to this kernel. So as I said, once we have this DBC condition, then turns out phi is invertible, and then it can be shown that M and Z are homeomorphic. Okay, so cast your mind back to definitions of homeomorphism that we talked about earlier. And moreover, if the underlying domain Z is itself a differentiable manifold in RD, but it could just be some set in RD itself. And if this mean correlation kernel is a smooth function of its arguments Z and Z prime, then moreover, it turns out phi is a diffeomorphism, i.e. that M and Z are diffeomorphic. Okay, so the story so far is that, at least under these various assumptions, the PCA scores are concentrated around a set, which set, this set M, which is homeomorphic or possibly diffeomorphic to the underlying domain Z. Okay, so that feels like we're getting somewhere, right? The PCA sort of point cloud is, in the case of homeomorphism, it's going to convey the topology of the underlying domain Z. And in the case of a diffeomorphism, maybe it's going to convey a bit more than just topology, something conveys some of the geometry of the underlying domain Z. And indeed, that's what appears if you start to consider more specific families of these mean correlation kernels. Okay, so if we suppose a particular form for this mean correlation kernel, okay, so for example, in this first row, supposing this mean kernel is just a function of squared Euclidean distance, and in the case where Z is itself a d-dimensional manifold, assuming this function f has a local maximum at 0, then it turns out that the geodesic distance in M, that is the distance of any shortest path connecting 2 points, is proportional to the geodesic distance in Z. All right. And for various other families of kernels, you get various other relationships between geodesic distance in M and geodesic distance in Z. Bear in mind, as I said, this is all in situations where, in general, we don't have no closed form expression for phi. Right? We don't have anything which allows us to write down a closed form expression for phi. But there's a connection that we've found here between basically correlation structure and the geometry of the point cloud, the geometry of the set around which the PCA point cloud is concentrated. Right. So back to some pictures to try and illustrate what's going on. Let's suppose that Z is a torus embedded in R3 and mu is the uniform distribution on it. So the torus is the wireframe thing here. I mean, the torus isn't just the frame itself, but the wireframe helps to convey the shape a little bit. And in this case, each of the fields is a Gaussian process, happens to be zero mean with this particular kernel. one of the ways that you can define a torus is in terms of the Cartesian product between two circles. Okay, so once I fix the location of the center of this torus and I've fixed the diameters of the tubes, then you can think of these two circles can tell me the coordinates of any point on the torus, right? And here I've just generated, these are 4,000 samples from mu. This is where they are on the torus, and they've just been colored by their coordinates with respect to these two circles. Okay, so it's the same set of points here and here, they're just colored differently to highlight their coordinates. Okay, so yes, we're in a situation where Z happens to be a manifold, and I've chosen that on purpose. Now let's see what we get when we sample from this and apply PCA. We get this. So in the top row and in the bottom row, it's the same sets of points, but again, they've just been colored differently. They've been colored with respect to these feature maps. Okay, and of course we can only sort of visualize 3 dimensions at once. So I've plotted PC1 up to PC3, and then 4 to 6, and then 7 up to 9. But a few things are immediately apparent. So the first is that, well, the coloring seems to indicate that the first 3 principal components, they seem to capture the distance this way around the torus, right? Whereas the principal components 7, 8, and 9, that's these ones, it turns out that they capture distance as is indicated here. So the distance around that circle that way. Okay, and so it's an illustration of the fact that the point cloud that you can get could be something quite abstract looking, but the geometry of it can be closely related to the geometry of the underlying domain. Okay, and in fact, some of you might be familiar with the TDA technique of persistent homology, where you do your barcode plots and so on. In order to detect topological features, if you apply that kind of TDA technique to these point clouds, right, you recover, as the RMAF says you should, the same topology that you do if you apply TDA to these point clouds, right? So indeed, that's in keeping with there being homeomorphism between here and here. And a bit more, our theory tells us that because in this case it's a simulated example where it was one of those radial basis function kernels that's just a function of the squared Euclidean distance. There's a proportional relationship between geodesic distance in the underlying domain Z and in the M, basically the set around which the point clouds are concentrated. So the red line is the relationship between those that the theory indicates, and the blue dots are what you get by numerically approximating the geodesic distance between the two. And one more example, I realize only just a couple of minutes late before we're supposed to go to questions. Let's think back to our discrete case. All right. Remember, I talked about this kind of situation as this kind of picture as an example of a homeomorphism. Well, in the case where Z is discrete, let's just say, for example, it happens to consist of 3 points A, B, C. You see that our FLV model it's a kind of mixture model, right? So the Zi can be regarded in this case where Z is discrete as an indicator variable, which tells you which mixture component that ith row of the data matrix comes from, right? So the cluster centers are given by these, and then we've got some noise which is added onto the cluster centers. And so all our theory applies to this situation as well, right? And so the the theorem that I showed you earlier about the uniform concentration of the PC scores in this situation tells you something about the behavior, a high dimensional behavior of applying PCA, or rather calculating the PCA scores in the context of mixture models, or at least this specific mixture model. Okay. And what you see is that when N is fixed and P grows, then the PC scores concentrate around the respective phi's. When P is fixed and N increases, well, things don't shrink in the other way, and that's in keeping with what we saw in the theory. If you remember, there were conditions that N had to be greater than or equal to something, and P on N had to be greater than or equal to something. So what we found empirically is that if you fix P and then you increase N, what you find is that initially when N is tiny, that helps in terms of decreasing this thing, which is just a error, basically the size of the error. But then as N increases past some point, that starts to sort of hurt you in terms of this particular error measure. And we think that's connected to what's going on here with these clusters being sort of a bit more diffuse. It's hard to say whether they're becoming really more diffuse, but our theory isn't refined enough to explain what's going on. That's just a different measure of the error. Maybe I'll skip that one. 2 more minutes, if that's all right, before Dan, if that's okay. This is sort of the take-home message slide, sort of to try to explain why this kind of thing is happening. So just a reminder, what was zeta I? It was what we got when we projected the ith data point onto the eigenvectors. Okay, but it turns out that there's a very simple linear algebra identity which allows us to give these PCA scores a different interpretation, and it's just this identity. Okay, that there's a relationship basically between the eigenvectors of y transpose y and the eigenvectors of y transpose. Okay, and it's just this relationship that's written here. Okay, and in fact that's a relationship which is often exploited for computational and numerical purposes when you're doing PCA in practice, but it's a bit of a different story. And the important point is that when we take this dual view of PCA scores, what we see is that we sort of step away a little bit from this interpretation of coordinates associated with projection, and we move towards an interpretation of PCA scores in terms of matrix factorization. All right, because if I multiply this thing by its transpose, okay, what we're basically doing is that we're getting a low rank approximation to this matrix. That's an n covariance matrix, if you like, or correlation matrix compared to the p by p matrix here. And what we're doing with this RFLV model is that we're basically implicitly stating a statistical model for this n by n matrix, which combined with Mercer's theorem is what allows us to get to the feature map phi. Okay, so there's a few questions which I took the liberty of preparing for myself, but maybe I'll stop in case anybody else wants to ask anything first.
Great, thank you very much. That was fascinating. Yeah, round of applause. I can see a couple of claps on the screen. That's all we get on Zoom. Thanks very much. Who wants to start with questions? I can see. So I've got Slido up. No questions on Slido right now. Go ahead, Anthony.
Oh, hi. Nick, that was really super interesting. So I had a question about some of the assumptions. So is the assumption that there exists that for any z prime there exists a psi such that those quantities are not equal? Is that actually a strong assumption, or is it a very weak assumption, or is it unclear?
Well, from a mathematical point of view, it's a sufficient condition for the feature map phi to be invertible. Right, and it's that invertibility of phi which is really, if you don't have invertibility, then you can't really say that you have a manifold there, right? Because you would have several latent points z which would get piled on top of each other. Okay. Now there's other more abstract but sufficient conditions for invertibility of phi that are out there in the kernel literature actually, but we thought that this was one which is, we liked it because it's saying something about this idea of correlations and sort of distinguishability by correlation. So whether or not it's strict in practice, it's that's kind of quite a context dependent question.
Okay, and I don't want to hog the time because I know Peter has a question, but you also assume that the xj are independent. Is that sorry, but it sounded like maybe you think that could be weakened.
Yeah. So basically what's going on in the last slide, I said that there's this n by n correlation matrix, which is the thing that we're actually studying, and the independence across the fields just as allows us to say something about concentration properties of that matrix. But if you had something like some form of weak dependence, I don't have the mathematical tools to say it categorically, but I think that's really what's all that's really important.
All right. Okay. Thanks very much. Anyway, super interesting.
Thanks.
Go ahead, Peter.
Thanks, Dan. And Nick, that was really fabulous. Thank you very much indeed. I congratulate you and your co-authors. Most interesting thing I've seen for a long time. I had to step outside while you were talking to take a phone call, so I might have missed this point. I apologize. Following your motivations, I was expecting to see what you called R, I think, the dimension of the PCA. I expected to see that popping out in the structure of the model itself. Now, I didn't see it. R, of course, has to be less than both N and P.
Yeah.
But I don't think you said anything else about it. Did I?
Yeah, that's right. So for the kind of concentration result, yeah, it's true. R is just any fixed thing that's less than N or P.
Yeah.
Okay. For the kind of all the manifold stuff, which is about how phi is a homeomorphism, what have you, R can be infinite. There's no conditions on R for all that side of it to work. So to be honest, what we'd really like is a similar concentration result where R can be anything, right? And we suspect what really matters is for the concentration is more something to do with like the decay rate of the eigenvalues rather than it being actually a finite rank and those eigenvalues dropping to zero at some point. But that's just not what we've been able to prove.
Yeah. So in practice, when you experiment with this,
yeah,
and you try different R presumably in data analysis, and you see something similar in each case, or is it really critical? Do you see these structures appearing visually for certain R and not for plus or minus one, or not?
Yeah. I mean, so it's a little bit case by case. There were two examples that I showed, talked about, which is a kind of mixture example, where calligraphic Z is discrete, and in that case, actually R is by construction of the model, R is finite, and it's quite black and white. It's all fine. For the torus example, that's a case where the R, which is of the kernel we've used to simulate the data, is infinite. Again, what we sort of see is that we think something to do with the rate of decay of the eigenvalues of the kernel shows up in basically the kind of size of the error that you're getting from truncating down to some finite R when you do PCA, basically. So we don't have anything detailed to say about how to choose R in practice at the moment. Yeah.
Okay. Thanks.
Great. Well, thank you so much, Nick. That was fascinating. I think in the interest of time, we will call it there, but I'm sure Nick will be very happy to chat about this if you catch him in the common room or drop him an email.
Yeah, sure. Just go and knock up here.
Yeah. Brilliant.
Okay, thanks very much, everybody.
Goodbye. Thanks.
Cheers, everyone. make sure you check out the other things that are going on this week. And see you next year for the seminar series. Bye.
Bye.